Hey everybody, welcome back to Math 251. In this video, we are going to talk about some limit applications and how we can evaluate certain kinds of limits using algebraic tricks and other techniques. So let's look at this first example. We want to evaluate the following limit, the limit as x goes to 2 of x squared plus 2x minus 8 divided by x minus 2. So the problem with plugging in x equals 2, that's our limit point, if we were to plug in x equals 2 here, we would get 0 in our denominator, which of course is not allowed in math. So we need to figure out a way to get around that. If you were to graph this function x squared plus 2x minus 8 divided by x minus 2, of course this function would not be defined at x equals 2 because it makes our denominator equal to 0. But that does not mean that we don't have a limit here. Even though our function is undefined at x equals 2, we will still have a limit here, and that's what we are trying to find. So if I look at the numerator here, I see that this can factor. So the numerator here will factor, and we'll get the limit as x goes to 2. This factors as x plus 4 times x minus 2. And then we have our x minus 2 in the denominator. Well, hey, look at that. This allows me to cancel these two factors. And I am left with the limit as x goes to 2 of x plus 4. Which is of course equal to 2 plus 4, or 6. So this is the limit of this function as x goes to 2, even though the function itself is undefined at x equals 2, since we still have that 0 in the denominator. So our limits here are the same. These two limits are equivalent to each other, even though the function x plus 4 is not the same function as our original function. Even though those functions aren't the same, we still have the same limit because this factoring allowed us to cancel some factors out and evaluate the limit without dividing by 0. Let's look at our next example here. We want to evaluate the limit as x goes to 0 of f of x if f of x is defined piecewise as x squared plus 1 for x less than 0 and x if x is greater than or equal to 0. So we have two pieces of this function, right? We could graph this function, sketch a graph, and see what's going on there. But let's try to do this analytically. So let's look first at the limit as x approaches 0 from the right side. So if we look at the right side, this means that x is slightly greater than 0, which means that we will be on our second piece here. So this will be equal to the limit as x approaches 0 from the right of our second piece, which is x. And of course, if I plug in 0 here, I get that this limit is equal to 0. If I look at the other side, the limit as x approaches 0 from the left, well, if I approach 0 from the left, this means that our x values are slightly less than 0, which means that I will be on my first piece here. So this will be the same thing as the limit as x approaches 0 from the left of x squared plus 1. And if I plug in 0 here, I will get 0 squared plus 1, which is equal to 1. So this shows me that I have a different right-sided limit than I do a left-sided limit. And when I have a different left limit and a different right limit, this tells me that my overall limit as x goes to 0 does not exist because I have a different number from the left and from the right. So the limit as x goes to 0 of our function, this piecewise function, does not exist. This is undefined because we have a different limit from the left and from the right. All right, and we have one more example. We want to evaluate the limit as x goes to 2 of the square root of 4x plus 1 minus 3 divided by x minus 2. So again, if we plugged in x equals 2 here, we would get 0 in the denominator, which we can't have. So let's take a look at this. I have a square root in the numerator. So I have the limit as x goes to 2 square root 4x plus 1 minus 3 divided by x minus 2. And when we see square roots in this kind of capacity, we should be thinking conjugates. because usually conjugates allow us to simplify things a little bit and cancel out terms that we want to cancel. So when I have this, I'm going to multiply the top and the bottom of this fraction by the conjugate of the numerator. Remember, the conjugate is the same term, except instead of minus 3, we'll have plus 3. So I'm going to multiply by the square root of 4x plus 1 plus 3, divided by the square root of 4x plus 1 plus 3. We have to multiply the top and the bottom of this function by our conjugate here. And what multiplying by the conjugate does is now when I expand these two terms with each other, our inner two terms will cancel, right? So let's see how that happens. We have the limit as x goes to 2. So multiplying our outer two terms, square root of 4x plus 1 times square root of 4x plus 1, that just gives me 4x plus 1. And then when I multiply my outer, that gives me positive 3 square root 4x plus 1. And then this gives me negative 3 square root 4x plus 1. So those two terms will cancel since I have positive 3 plus negative 3. Those cancel. And then I have negative 3 times positive 3, which just gives me minus 9. So that is why multiplying by conjugates is so helpful, because those square root terms cancel. And then on the bottom, I am left with x minus 2 times square root 4x plus 1 plus 3. Okay, well, I can combine some terms here in the top. So this becomes 4x minus 8. And then on the bottom here, I still have x minus 2 square root 4x plus 1 plus 3. And I can factor out an x minus 2 from the top here, or I can factor out a 4, in other words. So if I factor out a 4 here from the top, I am left with 4 times x minus 2. And check it out. Now we can cancel this x minus 2 with the bottom x minus 2. That was our problem term, right? That was a problem because if I plugged in that x equals 2, it made our denominator 0. So now that I've canceled that out, let's look at our limit again. I have the limit as x goes to 2 of 4 over square root 4x plus 1 plus 3. Now if I plug in x equals 2, I have no problems, right? If I plug in x equals 2, I'm left with 4 over square root 4 times 2 is 6 plus 1 is 7 plus 3. So this limit is totally valid. We no longer had to worry about a 0 in our denominator. So this is our answer here. So whenever we see a square root inside a limit like this, we should think conjugates, because that allows us to cancel out terms that we don't want in our limit. All right, that is it for this video. I'll see you later.